In 2022, India experienced severe early heat waves, recording the highest average maximum temperatures in 122 years. This chart maps the current trajectory. Driven by rising heat, India's total cooling demand is projected to grow by a factor of 9 by the year 2038. By 2050, cooling alone will consume 50% of the nation's peak electricity demand. The default architectural response to this warming environment is mechanical air conditioning, an attempt to lower ambient air temperatures by pumping energy into compressor units. This feedback loop of extreme heat and AC usage strains the national grid beyond capacity. We cannot construct enough power plants to mechanically outcool the climate. Surviving the coming decades requires a move away from mechanical cooling and toward fundamental building physics. The flaw in our reliance on machinery comes from a misunderstanding of biology. We equate human thermal comfort entirely with the air temperature setting on a thermostat. This diagram maps the science of comfort, a matrix governed by 6 distinct factors. While architects cannot control clothing or metabolic rates, they can manipulate 2 environmental variables without electricity: airspeed and radiant temperature. In hot environments, these variables are calculated using the Tropical Summer Index, or TSI. This formula combines ambient temperature, humidity, and wind velocity to measure the actual thermal sensation experienced by a human body. Empirical data from the TSI proves that humans maintain optimal thermal comfort without air conditioning as long as the operative index stays between 25 and 30 degrees Celsius. If we engineer building envelopes to manipulate airspeed and radiant temperature to hit this exact TSI target, mechanical AC becomes a redundant technology. Controlling air velocity indoors starts with the building's orientation. When prevailing winds hit a flat facade, the energy scatters. But when positioned at an angle of up to 30 degrees relative to the wind, the facade channels that kinetic energy into the structure. This demonstrates the squeeze point. Wind entering a small opening and escaping a larger one creates a natural vacuum, speeding up the air. But there's a limit. If the window-to-wall ratio exceeds 60%, the pressure differential collapses. Radiant temperature, the heat emitting from warm surfaces, requires regional mitigations, utilizing either thermal mass or shading. In the cold climate of Ladakh, high thermal mass is the solution. Builders utilize thick-walled earth architecture to provide insulation and slowly absorb solar radiation. In Rajasthan's heat, courtyard havelis use pressure differentials and reciprocal shading for natural cooling. Deep archways prevent the sun from heating the building's core. Long before HVAC, India's vernacular architecture proved that manipulating these variables yields mastery over interior microclimates. The Gokul dormitory in South India serves as a functional masterclass in tropical thermodynamics, maintaining comfort year-round with zero mechanical assistance. This blueprint reveals its protective envelope. The east and west walls have almost zero openings, acting as engineered thermal barriers against direct solar radiation. The critical feature is a ventilated double roof, an internal concrete slab, and a precast shell, separated by a continuous air gap. Solar radiation heats the shell, but the energy dissipates laterally, creating an 18-degree reduction in interior ceiling temperature. The architects also leveraged the surrounding landscape to create a continuous pressure differential. The north garden produces light, dry air, while the heavy tree cover in the south garden generates dense, moist air. This imbalance creates convection currents that pull cool air from the south continuously through the building. Gokul demonstrates that thermal comfort is the direct result of calculated structural geometry and environmental symbiosis. Moving from historical architecture to the modern urban environment requires applying these physics to high-density concrete blocks and low-income sectors. A field study conducted in Mumbai's Ward M and Ward S housing sectors provided an empirical test of these principles in a modern context. These are modern multi-story concrete structures operating in a warm, humid climate with zero mechanical cooling. Researchers gathered over 705 sets of continuous thermal comfort data from the residents to measure performance. This data visualization plots the outcomes. The buildings achieved an 80% thermal acceptability rate, with the vast majority of data points falling within the ISO standard Category B comfort zone. Despite the concrete construction and the intense urban heat, the data proves passive architectural geometry works at a municipal scale. A regression analysis of the Mumbai data reveals the specific performance baseline these buildings maintained. The passive design maintained a mean neutral temperature of exactly 28.3 degrees Celsius indoors. Occupants remained comfortable within an operative band of 24.6 to 32.2 degrees. Contrast this 28.3 degree baseline against the projected 9-fold increase in national cooling demand. Every degree of comfort achieved through geometry is a direct reduction in the exponential strain on the 2050 power grid. Integrating advanced passive building physics into affordable housing is the only mathematically viable way to survive the coming thermal crisis.